Hello, everybody. Hello, hi, teacher. I thought about doing this video in like one part with the explanation of the project, the challenge and the explanation of the topics. But I think I'd rather do them in like two parts in total, being less than 1 hour. I hope you don't mind. I may just unite them after. It's fine. I'll just do it like this. So I'm gonna start off before the project. I want to explain the topics. So we're gonna start off with electrostatics. All right, let's do this. Okay, so essentially what we have here is a case that is very similar to gravity and other forces in nature, because essentially electrons and charged particles are in the most explicit sense, literal small things that move through 3D space, and therefore some of the equations that are used to calculate how they behave can also be used to calculate are similar to that which we would use to calculate that of objects in the real world doing real world things like falling and being attracted to other things such as God, where are they? They were right here. It was perfect. No, don't tell me I lost them just for the presentation. Hold up. Oh my god, I actually lost them. That's crazy. I can't find them. Oh, there they are, under the table. Alright. I found them. Sorry about that. Like real world objects, or like magnets. There we go. These are going to be very nice for explaining things. Okay, so first off, the first concept that I would like to explain are electric fields. The equation, okay, this is going to be for later. Ignore this for now. Okay, so the equation for electric fields is E, which is the electric field, equals Q, no, the Coulomb constant times charge of particle 1 times charge of particle 2 over the distance r squared. Right here, this equation determines, wait, no, actually, I think I did it wrong. Did I do it wrong? Oh, dip. Yeah, I did do it wrong. I added an extra R. This is not. Okay, let me just delete it. Okay, here we go. The electric field is this equation right here. Essentially, the electric field can be defined as like an invisible sphere of influence around a charged particle or a charged plane or something like that, such as this magnet. This magnet, if it was a particle electrostatically charged, would have an electric field. And that means that it can interact with other particles which are also electrostatically charged. Magnets are not really as exactly like particles, because particles can be positively and negatively charged, whereas magnets have two poles, but it will still work for our purposes because essentially what they do is that they have a positive and a negative charge. These two, in this case, attracting like this, would be a positive and a negative charge. So we can multiply this electric field by the charge of the second one, Q2, and this would give us the electrostatic force, which is the K constant of Q1 times Q2 over R squared. And essentially what this does is that it indicates the force with which they will essentially expel, repel, or attract depending of the charge. If both are the same, they will not want to be next to each other. Essentially, what we're doing right now is that they are frozen in time and space. No time is passing. So we are measuring the force that with which they are interacting, even though they are not moving. This is essentially what the force that I feel right now with these magnets is the electric field. If they are both charged positively or negatively, they will separate. But if they are charged oppositely, that would result in a a a force that is negative, and that means that they would attract. The force with which they repel is negative, so that means that they don't repel, they attract. So that means that they get together. Now, that's the electrostatic force. And another thing that has to be explained is what was it? Okay. From this, actually, this is the beginning equation for all of electrostatics in some ways, because from this we can get something that is called the electric potential, which is denoted V, and it is also measured in volts, which is the electric field times the distance r, which is equal to K Q R instead of KQR squared. What this essentially says is the amount of this is a bit confusing. I must be honest. This is a bit confusing. And I will explain this one a bit later. Because to explain this one, first off, we have to explain two things. Number one, why is there a square here? First thing, the attraction with which things repel or expel each other gets weaker with distance. And this is the same phenomenon that makes uh, astro- um, uh, things around the Earth stay in orbit, and light get dimmer as you move farther away from it. This is the inverse square law. It's something that I learned quite a bit long ago, but I don't think I can't explain it honestly. But that's essentially why it's a square here. But to explain this square, we must also, to explain the V here, we must take this equation of the force and transform it directly into the potential. Like, oh no, one of the magnets fell. Oh no. Oh, that's not good. Okay, I'll look for it later. We have to take this equation and transform it directly into the potential energy. Because we must remember that this force is applied force. This is constant. But the potential energy is energy stored inside of an object, whether that be in the form of motion or height or whatever, but it is essentially stored energy inside of an object because of their distance with another object and the magnitude with which the charges are interacting with each other. So this will be K times Q1, Q2, R squared this time, times R. Why is this equation like this? Oh, wait, give me a minute. My dog is barking. I have kidnapped my dog, so she will not bother me anymore. You stay there. Alright. So, why is this equation like this? Well, we can remember from like basic physics that that the potential energy, no, that the work is equal to the force applied to an object times delta D. Yeah, good. This means that the work applied to an object, and therefore the stored energy inside of this object, is the product of the force applied over the distance. Work is the same as U. because U, W, P, E, and Ke, as I discussed with you another day, are all forms of energy that is stored inside of an object. So essentially, what we do here is that this is the force with which an object was taken and put close to another charged object with a specific charge, and we are multiplying it by the distance, because the distance is the amount of work that was required to do so. This is why, essentially, getting magnets closer and closer is harder, because the more distance it travels, the more work is required. And because of the fact that this is in function of r squared, if r squared gets tinier and gets below 1, the force would actually be increasing. So it would actually be like way bigger, and it would be way difficult to make them be connected if they are both positive, of course. And that is why U equals K QQ R squared R. But this can be simplified into U equals K Q1 Q2 over R. This is the formula. Now you may notice something. This is like a square. We have like this goes from this goes to this goes to this, and this goes to this. And actually, this is upside down. This goes in this direction, because in here, what we did is K Q1 over R squared. If we multiply it by Q2, we get the force. If we go the other way and multiply it by R, we get the electric potential. If we multiply this one by the Q, we get this. And if we multiply this by R, we get this. This is this. It's this amazing little thing. Actually, not little. It's actually quite big. It's a big relation between all of the formulas in electrostatics that show us this relation. And it's pretty amazing. Essentially, what we can see is that this is the final form of our equation if the distance between the objects is taken into account, and also if the charge of both objects is taken into account. The work is the energy that is used to put them in a certain place. And this I can now explain. Volts, I'm gonna let her go. She wanna say hi to her mom. This is why I do not like this. I do not like how this is generally written, because instead of writing it like KQ R squared R, they directly write it as KQ R. And this I do not like because it's confusing. It doesn't really make sense. Just like here. You could say that this makes sense probably, but it makes way more sense to say that this is work and this is the force. And the force is times the distance. So essentially this is simplified, even though it can be simplified. I think that more complicated makes it more easy to understand somehow. What does this represent? The U represents the energy stored inside of the object at a certain distance. The F is the energy stored between the two objects depending on the distance that was traveled. This is force. This is work per unit distance traveled. This is work per unit distance traveled. This over here, this is work. This is work per unit charge, because you have to multiply it by the charge in order to get this. And this is the base. So we have this diagram. It's beautiful. It really is. And that's essentially how I see electrostatics. It's just the forces between two particles measured, and then you either multiply by the distance to see how much force was required to put it there in function of the Q to get the electrostatic potential energy, Or you have the two Q's and you see it in terms of the R to get the electrostatic potential energy G as well. That's the first part of this. Now I'm going to explain Gauss's law and capacitors and all of that stuff. Yay! Alright, now to explain Gauss's law. We have the E is equal to, as we have already established, the constant K Q over R squared. That's our electric potential. What does Gauss's law indicate? Gauss's law is essentially a way to do this, but instead of it being just a point particle, so that it can be applied to other point particles at a certain distance with a certain charge, Gauss's law does it so that it's done over a surface. A charged surface, specifically, positively or negatively. And therefore, we can see the electric field lines. Because essentially here, we could see the little lines of the electric field here going into this. And we would calculate the force with which they are attracted by multiplying by the Q. And that's about it. But here, what we have to do is that we would see the lines over, if this is charged negatively. Let's say this is a donut with a negative charge on its surface. If it would be attracting all points with a positive charge to its surface, even if they were in here. So if this is 2D, it would be essentially the Gauss's law makes it so that the electric field is now essentially in terms of x and y in a plane instead of just the distance from a specific point. The Gauss's law can not only be applied to 2D surfaces, such as lines or planes, it can also be applied to 3D surfaces, such as this one. No. Oh, okay, wait. Okay, there we go. Just make it bigger. There we go. Such as this one. And essentially, this is what I'm saying. It is the electric field over the area in which it is found. This is a very small portion of the area, and it has an electric field. This plane could be divided into smaller areas, and would have an electric field as well. This sphere has a plane that is divided. It has this, as it is called, Gaussian surface, has a small. Okay, there we go. A small area which has its own electric field, and essentially, the Gauss's law essentially kind of makes it so that it's a sum of all of the electric fields found in these surfaces. Therefore, the equation for Gauss's law is depending on the shape that you have, because it could be just a square, or it could be with polar coordinates, or it could be a 3D Gaussian surface, double integral of the upper and lower limits of whatever you are measuring, the electric field. Oh, right. This is looping because it's a surface that closes in on itself sometimes, not all the time. This doesn't. The electric field times D, the small changes in A. This is essentially Gauss's law. Gauss's law can also be represented as Q, E, and C, the enclosed charge over epsilon of 0. That is Gauss's law. At least that's how I think I understand it. Alright, now that I have explained electric fields, potential energy, and the such, And apart from that, also the Gaussian surfaces a bit. I didn't explain it well, but I explained Gaussian surfaces and Gauss's law. We can now move on to capacitors. I'm gonna do a little drawing here. Am I recording? I'm recording. Okay, good. Do a little drawing. Okay, so a capacitor is essentially something that makes it so that electrons pile up on one side of the capacitor because of the fact that the other side is positively charged. There's attraction from this side to this side because, well, opposites attract. And generally, this is going to be connected to a battery. This is not how a battery is made in a circuit, but that, okay, this is the positive. Oops. Okay, so that's going to be how it's going to be made. And this circuit essentially charges the capacitor. But and there's many resources online, and you can find that something that determines how much energy the capacitor will hold is C, the capacitance of the capacitor. But question, how do we find C? Oh, well, you see, that's easy. We just have to take Q over V. Wait a minute. How do we get these? Well, that's easy. Again, let's start with Q. As we saw for the Gaussian surfaces and Gauss's law, this integral of the electric field over the area is equal to the enclosed charge over epsilon of 0. So we can calculate Q by taking this E, the electric field of inside of this capacitor, and we times it, we multiply it by dA. And this will equal Q over epsilon of 0. And then we can just put that here by multiplying by epsilon of 0. And essentially, this equation can simply be simplified to E times A equals Q over epsilon 0. And this can be made into E A times epsilon 0 equals Q. That's how we get Q. There we go. Now for the voltage. As we saw previously, the voltage can be calculated by multiplying the electric field times the distance. So essentially, instead of R, in this case, it's going to be E times ds, which is going to be the distance, this distance between the two capacitors, which can be simplified to simply E times ED. That's it. That's what we're going to do. So now that we have these two, equals V. So now that we have these two, we can take this. C equals Q over V equals, so Q was equal to E A epsilon 0 over V, which is going to be E, the electric field, times D. This is going to be our capacitance, but we realize that we can simplify the electric field because it's the same capacitor, it's the same electric field. So the capacitance is always going to have a formula of the area of the sheets times epsilon 0 over the distance between the sheets. This is going to be our calculation for the capacitance of a calculator of the capacitance. And that's how you do it. That's how you do that. I just did it. All right. Now, Give me 1 minute. All right. So now that this is explained, I'm going to have to explain them, their behavior in circuits. So let's make a new one. There we go. Now a capacitor is interesting. What you're going to do is that we're going to return to this version of the formula. C equals Q over V. This does it so that if we have either the voltage drop in the entire circuit or the charge of the individual capacitors, we can calculate the capacitance, or we can calculate the charge, or etc., etc. We can calculate any of these if we have two of them. So this is what we're going to do. Generally, we're going to take the charge as what we want to calculate. So Q equals CV. And in this case, there's going to be two cases for this. There's going to be capacitors in series and capacitors in parallel. Kind of a bad drawing, but you get the gist. There's going to be two ways of calculating here. For capacitors in parallel, the voltage drop across them is going to be the same. So essentially, if you have, for example, a 3-volt battery here that is connected to two capacitors, like this, two capacitors in parallel, the voltage drop is going to be of 3 volts in both of them. It's going to be the same. What is going to be divided is the current. Current is I equals... what was the current? Oh, okay. I equals RV. I think we're going to see this later. That's fine. This is going to be the voltage drop is going to be the same. So if we have the capacitance and we have the voltage, we can calculate Q by simply adding up the capacitances of the C1 plus C2, the capacitance of each capacitor, times V is going to equal Q in parallel. This is in parallel. Now for series is going to be different. We have our same 3-volt battery, but now the capacitors are connected in series. Wow. Essentially, what we're going to do here is that instead of doing this directly, we're going to calculate V instead. And V is going to equal Q, because before, over here, the voltage drop was the same. In parallel, the voltage drop is the same, so we can multiply by these. But in series, the voltage drop is not going to be the same. It's actually going to be divided against these two, like the charge was in these two. So the common factor here will be the charge. So what we're going to want to do is essentially, like, if you have this, you're going to do V equals, you're going to take this one over here, and you're going to do Q over C. This is the equation that gets derived from this one, when Q is the constant. And therefore, what we're going to have here is the capacitance of these two over 1 added. This is going to be added up, and that's going to equal our voltage. Yeah. And so we can also say that when they're in series, the total capacitance is equal to the sum of the inverse of the sum of the inverse of each of the capacitor's capacitances. In parallel, it's going to be C total equals just the sum of the capacitances of the capacitors. And that's about it for how they work in series and in uh, in parallel. Now we're going to look at resistances because it's kind of the same, but it's a bit different. Shocker. Resistances are essentially the opposite of capacitors. You're going to have wait. Okay, we're good. It was kind of dying for some reason, but I think it is because I didn't have enough RAM. Okay, so now we're going to do resistances. Resistances are essentially calculated with Ohm's law. Ohm's law says that the voltage is equal to the current times the resistance present in the circuit. In this case, we can see that voltage is actually the one that is isolated instead of it being charged. So it's going to be the opposite than in capacitors. We're going to have for parallel, okay, we're going to have our battery, and we're going to have two resistances in parallel, like that. They're going to be in parallel. They're going to have a certain ohm, a certain resistance. So essentially here, what is going to happen is that we can see is that we are going to take the I is equal to right. Okay, wait. In this case, hmm. Hmm. Okay, yeah. Okay, so we're gonna have I equals V times. We can change this actually directly into I equals V over R, which means that in this case, the current is going to be V times the sum of the inverse of the sum of the inverse of the resistances. The opposite as for capacitors, because this happened in series. Here it's happening in parallel. And for series, we're gonna have our little thing here. This is gonna be how it's gonna be done. And then we're gonna have our formula here. It's going to be well, yeah, exactly this actually. V equals IR. So it's just going to be the voltage is equal to the current times the sum of the resistances. And that's how we're going to calculate in series and in parallel for resistances. I forgot to mention. So essentially here, the total resistance is going to be equal to this. It's the sum, it's the inverse of the sum of the inverses of the resistances. Ah. 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 No, what happened? Oh shit. Oh, I selected white. Okay. There we go. That's going to be the resistance for parallel, and for series is just going to be a sum. There we go. Now, why would we want to do this? It seems interesting to just want to do this. Why would we want to unite these into different ones? Well, that's because circuits are generally not made up of just resistances or just capacitors. Generally, they are made up of both. So, what is going to happen is that we can take these sums and these sums and turn them from a circuit that is quite difficult. Honestly, I'm not gonna. Okay, let's just. We can take them and turn them from a circuit that is quite difficult into one that is simplified into just a power source, a resistance, and a capacitor. And from this, ladies and gentlemen, we can derive the power that this system produces for something. For example, instead of this being resistance, we can replace it with a flashlight or a bulb of light that produces light and has a resistance of a certain resistance when electricity passes through it. And essentially, what we're going to want to do, for example, in these types of circuits, is make sure that the power supplied is enough, and also that maybe the capacitance is at its minimum, so that the flash lasts the least amount of time, but also make it so that the power is not too much, because then it could blow. It could blow, and that's not good. And the formula for power is voltage times current. And there we go. That's our formula for power. And it derives and it makes watts. But something interesting can happen, because this is a constantly powered circuit. What if the battery were to be removed? Well, in this case, what would happen is that actually the capacitor has already become charged before the battery got removed, or just taken out of the circuit, even if this is still connected. So this has a very small charge, or a very small voltage drop that will be applied to this. Ignore that it's dead, but will be applied to this light, and therefore we will see that that it will last a very small amount of time, have a specific current because of the sum of this, and the voltage will also be different because of the voltage drop from here to here. What is the use of this? Let me present to you a camera. And the most important part at the moment, the flash.
Oh my God!
All right. With all of these concepts explained, we can begin with the challenge. All right. So, now that all of the concepts have been laid out in paper in front of our eyes, we can initiate the challenge. In this challenge, the evil cuco company. Wait, I have him right here. He's so evil and rich. Look at him. Look, he is. Look at him. He's so evil and rich. He's so pretentious. It's not okay. But okay. The evil Cuco company wants us to wants to pay us minimum wage to create the most efficient flash with the least amount of components. So, what are we gonna do? Based on what we have learned, we are given. Wait, actually, let me just open up the. Where is it? The challenge. Hold up. Wait a minute. Hold up. Wait a minute. There we go. Take this, put it right here. What we are asked to do here is create an efficient flash with a maximum which has these parameters. The maximum electrical potential difference of our flash, of our circuit, I mean, has to be, will be of 100 volts. That's the source that will be providing for our capacitors and our flash. For capacitors with a capacity of 200, it was micro? Yeah, microfarads are given to us, and they can support a maximum electrical potential difference of 120 volts. That's okay because our maximum potential difference is of 100, so we don't need to worry about that. So that's fine. But here's the kicker. An incandescent electric bulb with a resistance of 16 ohms. This is not good. Not only that, you need a maximum power of 200, 25, 2500 watts and a minimum of 1300 watts. And last but not least, we need to make it so that it lasts the least amount of time. A 1/1000th of a second at most. This cuco man is crazy. I am telling you. So this is our report. We have here the abstract, the introduction, yada, yada, yada. We lay out all of the information like I just did. And this is the equipment, the experimental setup. So this is what we're going to do. First off, we're going to arrange the capacitors in such a way that the capacitance is at a minimum so that the time that it flashes for is also at a minimum, but it also doesn't pass over the limit and burns our light bulb. Through experimentation, we found that the best array for these capacitors was this one. 3 in parallel, and after that, 1 in series. We could have done all of them in series, which in total... Oh right, I almost forgot. It would be this to the -1. We would have a total capacitance of 50 microfarads, which is very good. It's very much the smallest capacitance that we can have. But a problem arises. Once the 4 capacitors are charged, they will all have the same charge of 100. And since they are all in series, the total charge of... Okay, so essentially, we can realize that if we were to have 4 potential differences of 400, we would have 400 squared over... What was it again? All right, the resistance, which is going to be 16. And this would be 10,000 watts of power, which is not good. The power formula is the voltage squared over the resistance. And we can only have at most 2,500, which is not good. So what do we do about this? Because of the array that we chose here, the potential difference here and here will essentially be that of just 2 capacitors. So we're going to do that. I mean, yes, the potential difference will be of 2 capacitors. So instead of being 400, it's going to be 200 squared. And that, voila, equals exactly 2,500 watts, which is perfect for our purposes. And that is what essentially happens. This is the least capacitance that we can have while also having the most watts generated. We could also, in theory, make it so that it's 2 in parallel 2 times, and then it would be the same power, but the capacitance would actually increase because it would be 200 times here, it would be 400, and it would be 200 microfarads instead of 150. So this is the best array that we can have for our purposes. After that, what we do is that we take the power and we use the potential energy. We replace it with this formula, which is also a formula for the potential energy in capacitors, only in capacitors. It was mentioned up here, if I'm not mistaken. Around here somewhere. God damn it, I don't think it's there. That's fine. So essentially, this is just the formula, a formula for the power generated over time over, the du over dt. So we're gonna do this whole thing, and in the end, we're gonna get a power. We're gonna find out that this is the formula that is left for the power in terms of t. With this expression, we can figure out how long it lasts and how long it actually needs to be turned on, how long the bulb will last. For that, we just equalize it to 2,500, or in this case, 1,300, which is the minimum amount. And we can see that t is equal to less than 0.001 seconds, or 1 millisecond, which is under the time that was demanded. And therefore, we have achieved our goal. We have managed to create a capacitor of the most power possible and the least capacitance possible that is under the time that should flash for less than the time that Mr. Evil Cuco asked us to make it flash for. And that's it. I didn't explain it very well. I'm sorry. That's because I understand these formulas a bit less than the first ones, which I did explain very well. But that's essentially what we did. We just took what we had, we put it in a specific array to get the capacitance and the power, and from that, we used this formula of potential energy in terms of T to see how much time it would flash for, because we already had the power it was producing. And that's it. That's our flash. Thank you very much for watching. I hope this is good enough. I will be now doing the other 2 videos for the extra points. Have a nice day, teacher. Have a nice night, actually. Thank you very much. Thank you. I love you. I have always appreciated being with you in these semesters. You are very nice, very kind-hearted. Even though your style of grading is a bit interesting, I really like that you give us many chances to reconcile for what we do and what we don't manage to do. I'm very happy to be with you because my other friends, they're with another one called Escamilla, and he's I don't want to be with him anymore. I don't want to be with him anymore. He's I don't like him, but you I like very much. So thank you for being my teacher this semester. I hope you enjoyed this video, and the next ones I will make. Goodbye.